Welcome to a lesson with Dr. Powell. Let's take a look at a few different types of discontinuities. That means places where a function might fail to actually be continuous. One simple one is a function is continuous except for at a point, and if that point is just simply a hole, then this type of discontinuity at that point is simply, well, it's not continuous just because the point's not in the domain. The function is not continuous outside of its domain, I guess. But really, I just drew a function that's continuous on its domain. But people usually call that a point of discontinuity in a calculus course, but really, the function's still continuous on its domain. But if I were to put like a point right here, okay, so then the domain goes from way over here to over here, including this guy or this x value right here. Notice that now this is in the domain. This value, the x value right here, let's call it a. X equals a is in the domain, but it's not continuous there. But we're going to call this, in this particular case, a removable discontinuity. Why is it removable? Just simply because we just need to change what the value of y is at x equals a, and just a simple change of the what the y value is will guarantee that it is continuous. So we're going to call that a removable discontinuity if you see that. All right. Now, for a function, we could also have something like this. All right, maybe we come up and then you might see, now what's this? This looks like a jump, right? Well, call that a jump discontinuity. But, people might call this a jump discontinuity even in the case where what we're looking at is if this is like just a hole, they might even call that a jump. But technically speaking, this is just a point outside the domain again, and that's pretty much it. But I think a proper terminology would just be to call it a jump when it is actually defined right there, but either way is fine. So that would be a jump discontinuity. But you want to be a little bit technical. Perhaps the function, as long as the function is like narrow, maybe there's a lot of different points. Maybe the domain is not continuous line or something, or line segment. Maybe it's just like pixelated. These are just points. That's still a function. Just doesn't only has certain points in the domain. And as it goes along, maybe the points are narrowing in on a y value, and they narrow in a particular y value. From the other side, they narrow in on another y value. We can also call that a jump as well. Okay, so jump discontinuity, removable discontinuity. And if you like, sometimes people call things like this, going up one way forever and going down one way forever. We would call that maybe like an infinite discontinuity. Well, really, if I put a point right here, then I would say that the function is discontinuous right here just because it's defined there. It's in the domain, and of course it's not continuous. It's not connected from across right here. But they also use the term infinite discontinuity even when the function is not defined on that asymptote line. Okay, so hence you can call that an infinite discontinuity if you like. I kind of have to think of this as after doing an infinite squash, like really this is a function coming up. Like if you take the whole y-axis going up and you compress or do some kind of transformation on it, like even taking reciprocals. Reciprocals take the intervals, take the intervals from 0 to 1 and take all the reciprocals you get. You actually get the number line all the way out to infinity, from 1 to infinity. Like this part and this part are actually mapped to each other perfectly by this reciprocal action, like taking a number and finding its reciprocal and vice versa. It maps perfectly onto it. So using that kind of mapping idea, we can picture the interval from 1 to infinity actually as this interval from 0 to 1, where the reciprocal infinity actually would be 0, but it's not. But if we want to include 0, then all of a sudden it's kind of like we're including infinity forever, but kind of in a finite picture. So if we squash it, like take an interval like 0 to 1, like in a squashing mechanism, you could think of this as being like, you could even fill it in. It's usually not filled in. In fact, it's never filled in. But you think of it as an open circle. Think of this as an open circle too. If you kind of squash that, and maybe if this is kind of label it, you squashed it, but this point right here, consider it as infinity or something like that, or negative infinity, and this guy right here as positive infinity. In that particular case, you could even think of an infinite discontinuity like that as simply just being a jump discontinuity if you want. So these are some common notions in a calculus course for types of discontinuities that you might see. But yet there's another one here which is also, which is also talked about. So something that's oscillatory, something that's kind of moving up and down way too much. Like, if you have a sine curve and it's getting rapidly forever, oscillating way too much, like the limit of how much it's oscillating to a point is going up and down too much. In this point, the y values, as I head in this way, are actually not ever getting close to just one particular y value. It's moving around too much. So this is another place where function would fail to be continuous, as well, the limit of the function doesn't exist to a point, so it's continuous if the limit to a point is equal to the value of the function. If the limit doesn't exist to a point, then it can't be continuous there at all. There's no y value here that we could assign, so we kind of have to say that would actually make this continuous as we head in closer. I mean, if maybe we're heading into a point and this is kind of oscillating right to that point, up until that point, but not quite getting there. A good example is something like, of course, my example actually comes from the other side, but it's sine of 1 over x, and if you want, you can even, the sine over 1 over x is a good example of that, because 1 over x, what happens as we go, in fact, it works from both directions, because what we're doing, what is 1 over x? That's like a reciprocal idea. It's taking something like way big, like going off to infinity, and it's bringing it in close to infinity. Now becomes going to 0 in a short little space. So an infinite number of oscillations in just a finite little space. Yes, it'll oscillate way too much. And notice that you can't plug in 0 into here, so this function is actually not defined as a whole at x equals 0, but where you don't really know where to put the hole, so it's just not defined at that point, and there's no way of having a hole to fill in. So there's going to be a point of discontinuity right there. We can call that an oscillatory point of discontinuity. Thanks for watching.